Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Clement Schiperski. I'm an architect in CSD, and today it's my pleasure to have Andreas Gall visiting us. 2 weeks ago, I believe, we had Michael Franz talking to us about trace-based compilation at large in general. And Andreas has actually done all the work, so he actually knows how it actually works and can tell us about that. These two talks were coordinated, and so we should be able to connect to where we left off. So it's my great pleasure to have Andreas today here, and I was also asked to announce that there is a DL for those of you who want to discuss the topics that come up around trace-based. It's called TraceJIT. So if you want to actually subscribe to that and follow what's going on here. All right, thank you. Thanks, okay. Andreas.
Thank you very much. So I will talk today about trace-based compilation of JavaScript. And in particular, what I will try to do with my talk is motivate why I think that there's a difference between compiling statically typed languages, which we have a great deal of experience with, and dynamically typed languages like JavaScript, which you have somewhat less experience with, at least somewhat less success in many commercial products that you can buy these days. And I will then talk specifically about the approach we are taking to compile dynamically typed languages using trace trees and trace compilation. And then I will conclude with some benchmarks, and I will show you a little bit how we compare to other approaches. And also I will spend some time on trying to explain where I see future path to even more performance in these kind of systems. But first, I think before we should talk about dynamically typed language compilation, we should understand why it's important. And if you look at the way applications are changing right now, there's certainly a strong trend towards having more network-connected applications provided to you through a web browser in a web setting. And this started out with applications that are pretty much mostly exclusively useful in a web context, communication suites like Gmail or Meebo, actually some IM system. But it's Zimbra is also a productivity suite, Outlook-like. But it's also moving towards applications that are not really as traditionally understood as to being a communication application for the web. So there's Google Maps, Google Docs, Google Spreadsheet. Most of these things are not really competitive yet with full-blown like Microsoft Office platform. But there's certainly a desire and a tendency towards providing more functionality there. And it looks like the browser is becoming as a future platform to be able to run these kind of complex applications. If you look at the languages that are being used to build desktop applications and to build web applications, they're starkly different. So in desktop, I looked up some statistics on the most frequently used languages. They use some time-based rating, which languages are hip, and I think mostly it's based on queries and search engines. And Java is very popular, and there's of course C, C++, just this huge body of legacy code. C#, Delphi, these are the kind of the top picks if you write applications today. And if you look at their nature, they're basically all very similar. Some of them is object-oriented, some of them are not, but conceptually they're all very similar in their type systems and underlying concepts. If you look at web servers, you already have a very, very significantly different set of languages being used. It's mostly dynamic languages like PHP, Python, Perl, Ruby. There's of course still some C, C++ around. It's like old common gateway interface, but that's mostly going away. And there's also of course Java, which has its own gateway interface and runs in web servers. But the emphasis seems to be on, especially on the side of like rapid development on like PHP and Python. And it's also active server pages. But the concept is really dynamic type languages seem to be preferred, especially if it's about rapid development. The browser side is very similar. You have JavaScript, ActionScript, which is basically a JavaScript dialect, and then Java, Silverlight, and C, C++ through ActiveX plugins. But I think it's fair to say that most dynamic web content is driven by dynamic languages. At least today. And if you look at future trends, it's very unlikely that's going to change. So Java is basically on the way out of the door. It has a very large footprint. It's really slow to start up. Some of you might not remember the last time you saw Java on a web page, just because it's so rarely used these days. But if you think back of your last experience, it was probably watching a little ball spinning as the JVM is starting up. So there was just this large latency startup problem that people didn't like. And There's also like other native code plugin systems like ActiveX, which security-wise really a problem, and they're also basically going away. It's similar on the server side. CGI and C code running in web server is security-wise pretty sensitive. So that's kind of dying out. Java seems to have a good foothold there, but at least on the client side, it doesn't seem to pick up anymore. And what's I think most surprising to me in the space is the fact that there are better stories available than Java for the browser, through Silverlight, for example. And they actually have very good tools coming with them. So there's this famous Silverlight demo where the two chess players, two automated chess algorithms, are playing against each other, and the Silverlight version of it beats the JavaScript version by quite a bit, because it's so much faster than executing JavaScript in Interpreter back then. And on top of that, Silverlight has very superior tools, nice IDE integration. A lot of that story in JavaScript is very sketchy. You have different tools. You have to edit text files. You have to upload them to browsers, to web servers. And despite that, and on top of that, there's also a lot of vendor incentives to actually use these technologies. And all these things together still don't seem to be creating a rush towards Silverlight in this case, for example. It's still a lot of JavaScript, PHP-ish content out there. So if this is the case, if you currently have a lot of dynamically typed languages driving web content, and this is unlikely to change dramatically overnight, what is the state of the art of JavaScript performance, and how efficiently are these applications executing? So before I answer that for today, let's go back to June 17, 2008, which is not even 6 months ago. Back then, when I looked up the statistics, we had 1.4 billion internet users, according to some statistics, and 95% of them had a browser that supported JavaScript in some form or shape. And back then, not even 6 months ago, JavaScript was a purely interpreted language. It didn't matter what browser you use. It was always an interpreter. And there were also actually very few contenders that would even try to do any kind of compilation. There was Rhino. This is a JavaScript JVM compiler. Basically, this gives you the disadvantages of both worlds. It gives you the funkiness of JavaScript combined with the slow startup of Java. So that was not really something that would be useful for a browser. But it has actually some use on the server side. I think actually Google uses internally quite a bit for server-side JavaScript applications. And then there's Tamarin. Tamarin is Adobe's virtual machine for Flash. And ActionScript is a superset of JavaScript, and actually it's a typed superset with optional type annotations. And that VM actually did some compilation. But again, it was geared towards ActionScript, which is a typed language. So it's really a Java VM that can run JavaScript syntax. As a result, you get pretty good performance, acceptable performance for typed code, but very poor performance for untyped code, which it was not optimizing for. So actually, Tamarin was slower than the interpreter that Mozilla was using in Firefox back then. Something like 2 months later, Mozilla released the first Firefox build with a JavaScript JIT compiler in it. And this is the TraceMonkey project. And the speedups are in a range of 2x to 20x. I will talk later in the talk a little bit more about which cases are particularly sped up, which are more difficult to compile. But I think the key point to take away from that experience for me was that I was absolutely astonished by the amount of press coverage we got. And that was somewhat surprising because JITs have been built before. And just as an example, my parents live in some small town in northern Germany. And in the local newspaper, they were reading about Mozilla and Firefox and JITs. And I think it was very surprising to me that there was a lot of like non-technical media covering it. And that just shows that people care. And web is something people can connect to. And everyone has a web browser. And everyone used it. And everyone knows Gmail or some other webmail. So they can kind of relate to this technology better than they can to like desktop JIT. That's fairly transparent. But a web browser making web applications X times faster, that's not something that people can relate to. And of course, the competition wasn't far behind. September 1st, Google released Chrome, or Chrome released itself from Google. And it's completely a VM completely written from scratch. It's probably an estimated 2-year effort or so, looking at their timestamps in their code base, and it's marvelously engineered. It is really great on their own benchmarks that they released this V8. It's kind of a mixed bag on the established benchmarks everyone else was using at that time. I have a couple of numbers for that as well later on. And then not even 3 weeks behind that, Apple released Skillfish Stream, which is their particular take on how to do JIT compilation. And that provided basically a 1.5 to 2x speed up over already very, very fast interpreter, which was already to begin with about 2x faster than Mozilla's interpreter. Part of that speed up is in the regex JIT compiler, so I think it's really closer to 1.5 speed up than 2. But still, it's a substantial improvement. And I think the key questions from this motivation to take home is, why did it take so long to make JIT compilation happen for JavaScript? Like Hotspot is 10 this year. There's so much research on self and similar dynamic type languages. Why did it take so long to get JavaScript compiled? And also, why is the state of the art for so many other languages similarly poor? If you look at Python, there's PyPy, Parrot for Perl. These are all nice efforts to add JIT compilation to dynamic type languages, but most of them kind of got stuck along the way or don't really offer all that great performance. So what is the difference here? Is it really so different compiling a dynamically typed language from compiling a statically compiled or statically typed language that there's some inherent complication that somehow makes it more difficult to do this task? And that would somehow explain why it has taken so long to actually do that. So let's look at some statically typed programming language snippets and compare them, what they look like in a dynamic typed language as JavaScript, and then I will try to show you from a compiler builder perspective what the resulting machine code is if you actually compile that. I'm using Java in my slides as an example, but you can basically substitute any kind of statically typed language. You can basically almost substitute C# for the syntax or C even. So if you look at simple expressions in Java or C or C#, the form of like A plus B equals assigned to C, then all these variables are defined with a fixed static type at compile time. So as I edit my program, I have fixed down the fact that A, B, and C are all integers. And even more, on top of that, I actually also have defined the semantics of this operator, of the plus operator, which says that if you're adding two numbers, you add them in an integer fashion, and if there's an overflow, the overflow is going to be thrown away. This is very nice because this is a very close match between the semantics of the language that it prescribes for these primitive types to operate on and the actual machine code I'm generating. So depending on whether these values in this for these variables are currently in memory on a register, I have to load them from memory, but otherwise basically the entire addition is literally just one machine instruction, something like 2-3 bytes of machine code I have to generate for this expression. And even more importantly, as long as register pressure permits, I can actually take these values and directly put them into a physical register, because I know that I can put types, the integer type, into a physical register, and I can completely represent it there, and I can represent every value I can possibly put into A into a physical register. So it's safe to always maintain it in that physical register. Now let's look at JavaScript. Basically, from a syntax level, the only difference we will see is that now the int is replaced with var. JavaScript is dynamically typed. So all I say is I have three variables, A, B, C, and I will operate on them. And I will not tell you what the types are. You can figure it out as you go along, as you actually do the operations. Then we will decide what actually the result is and what the type of the result is. And of course, this is much more complicated to implement. So I've shown here an overly simplified version of the interpreter implementation of the plus operator in SpiderMonkey. So the first thing we have to do is, since we no longer have information on the actual typing of A and B, we have to dynamically discover the types at runtime. So frequently for this JavaScript or dynamically typed language, interpreters use basically this type dispatching. So they check, is A an integer? And is B an integer? And if so, I can add them as integers, and then I have to box them back together. And I will explain in a second what that means. In addition, though, since the semantics language is different now, I cannot simply throw away overflows. So if I want to add two things as an integer, in addition, I have to check, make sure that no overflow happens if I add these two values. If that happens, I cannot add them like integers. I have to add them like doubles. Now, on top of that, now since A and B have not a predetermined type, I have to now carry the type around somewhere as well, and actually have to encode that into the value itself. So now both can change, the value and the type of variables. For this, actually, I encode both pieces of information into the variable storage location. And every time I do an operation, I have to unbox these values, so take the value out of the box, add them together at the value level, and then the result I have to put back into a box, and then that's what I store into the variable. And then you do this for integers. If it's double, you do this for doubles, and it's for strings. And so strings actually get concatenated, not added numerically. And then there's a whole bag full of really complex cases, like left side is a Boolean, right side is undefined, null. The entire implementation is hundreds of lines of C code, just for the plus operator alone. So if you compare this with the complexity of the one-line machine code you just had, you will notice how stark the differences are between these two worlds. Boxing in this JavaScript virtual machine we are using at Mozilla, SpiderMonkey, is very similar to the old Lisp machines. Basically, you have a tagged integer that can store 31-bit small integers by setting the lowest bit, z, down here, to 1. And the rest of the word you can use to actually represent numbers. And then if that is set to 0, you can represent the remaining types by boxing them into a heap object. So even doubles, or floating point numbers, are represented through a heap object. You have a pointer into the heap, that's where the actual double is stored. And the pointer itself you store in the upper 31 bits. And all the operators in JavaScript actually have now different semantics depending on the 1 or 2 or 3 operands that they take. And depending on how you want to count, you have 5 to 7 types in JavaScript. And this means for anything like binary operators, the number of combinations you have there is really large. And you have all these complicated rules how to deal with them. And we have this strong difference between the 2 bytes of machine code against hundreds of bytes of source code. This does not only affect low-level operators in the language. So similarly, if you look at classes in something like Java or C++, very similarly, if you define a class and you give it a property, field A, you define the type of it as being int. And this field A in the class can only store integer values. This means that if you allocate an object of type X and assign 1 to that field, statically at compile time, you know exactly the type of X. So you know exactly what offset into X's memory representation at runtime you have to go into to write that value. And you don't have to store the type because it's statically given. So it literally translates to this one machine instruction where you can statically at compile time pre-calculate the offset you have to reach into X, and then you add something to the base address of the object pointer, that offset, and write the value in it. So essentially we ended up again with one machine instruction. Now in JavaScript it's a little bit different. In JavaScript we don't have classes. What we have is objects, and that's really just a glorified name for hash tables. And we can define these hash tables and we can put properties in there. And to make things a little bit more interesting, we can put these objects or hash tables into relationships with each other by using a prototype chain. So I can say I have 2 objects I declare here, X and Y, and both have a property A. And X has the value 1 for A, whereas Y has 2 for A. And I can now say that Y is the prototype of X. This means is whenever I access X and I'm looking for a property, if I do not find it locally, I will walk this prototype chain to Y and try to look it up in Y. And if Y has a prototype, I will continue walking that down there until I at some point have no more prototypes to walk. So if you do something like print x.a, this means I go into X, try to look for property A, I found it, great, value is 1. Now I can go ahead and actually delete that property, x.a, hash table, removing an entry from the hash table. Deleted that property, and now you print x.a. We will now look at X. A is no longer locally present, so after we have not found it, we go to Y, there we find it, so x.a is now actually 2. So you can emulate a lot of constructs like inheritance with this mechanism, but you can see that at a semantic level, it's quite different. And if you have to compile code like this and you have to take into consideration all the corner cases, it's quite a bit more difficult to do that. So this means that if you write down something like x.a, which is very cheap in a Java world and looks easy enough to compile, in JavaScript it really means that what you end up with is this like complex loop where you have to look up properties. If you find them, you return the value from the local object. If not, you have to keep walking this chain of objects in a loop. This gets even worse now because we don't even have the property names don't even have to be statically pre-calculated atoms. They can be just arbitrary strings. So I can say x equals y, and A, x plus x equals 1, which means x plus x is a string concatenation, so the result is yy. So the yy property of A becomes 1. So I can then, in the next line, a.yy access a property and get a 1 back. So this means not only do I have to have this loop where I look in different objects, it also means that this offset off idea where I figure out at what location in the object do I find my field or property, I cannot necessarily do that at compile time. I have to do that dynamically at runtime. So I give offset off a string, and it will tell me a certain slot location. Yet it can get even worse than that, because arrays, which we know in the Java world as to be something very efficient, where we have a sequence of integers in this case, where we can store values in, very easy to access, right? We check the length, make sure we don't write beyond the allocated area. So it's basically one unsigned value comparison. one branch to throw an exception if something goes wrong. Otherwise, we can emit straight a machine instruction which takes the base address of the array. It takes the index, multiplies it by the size of the words, plus maybe some offset to skip over the header of the array. Essentially, it also boils down to just like 3 machine instructions. Very compact, very fast. And even worse, authors are used to Java and learn Java in their education. Basically, this is what, when they see the syntax, y equals x, and they internally it tells them this is fast. Now, let's look at what JavaScript does with this. In JavaScript, arrays are objects, and elements of the array are properties of the object. So I can generate 2 arrays here, x equals 1, 2, 3, and 4, 5, 6. And what this means is that x is an object that has a property at index 0 of 1, and at index 1 a 2, and at index 2 a 3. And I do the same with y with 4, 5, 6, and then I can again use a prototype chain. So I can say x is now the prototype of y, and if I look up the first element in y, we look into y, we find, I'm sorry. At least it's my phone, not someone in the audience. So we look up the first property of y, and we find it here at this location. It's a 5, so we print that. Now, just as we did with regular properties and objects, we can actually delete that property and deleted the 5 here. And now if we access the first element of y, we will look into this object, and we will see that there's nothing here. This is called a hole. So now we follow the prototype chain and find the 2. So at an implementation level, this is vastly different from what you would expect in a statically typed language like Java when you access arrays. So now basically you have to follow the prototype chain. You have to represent holes. You have to be able to represent different types in this array. It's a lot more expensive to implement that. Now, where we want to get to, where we really want to compare ourselves against, is of course statically typed languages. We want to be as fast as Java or as fast as C. And at least for certain cases, we already achieved that. We have this like infamous simplified hello world example where you have an empty loop counting to a large number. And on the release day, the VP engineering Mozilla actually did this little benchmark that he blogged about. And he took here GCC, wrote a little snippet of C code that does this empty loop in C, and compiled it with GCC and executed it. And he's measuring the pure execution time of the loop, not the compilation time with GCC. And we get something like slightly below a second. And then if you do the same thing with our trace compiler, then basically you use the same code as JavaScript code, run it, and this now is including JIT compilation time and all the overhead, you get about 1.07 seconds. So it's pretty close to what the C compiler does with this. Now, for full disclosure, the C compiler was invoked without optimization here. And it does not really do a lot of resource allocation on it. If you enable optimization flags, the code speeds up quite a bit. I would say it's at least 2 or 3 times faster. But even if it's 2 or 3 times faster, getting within 2 or 3x of C is pretty good. Comparison that previously it was like 50x. Yes?
Why don't you C code speed up to not to 0? Because it's a big no.
If you optimize it, it might actually do that. On the other hand, I think most C compilers don't optimize empty loops because people tend to write them for a reason and have some poor man's delay loop. So I don't think it would go to 0, but it would certainly get faster, better resource allocation. So our trace compiler does a lot of specialization. I will talk a little bit about the things we do on trace. It's nowhere near as efficient as GCC in all cases. So I would expect at least a 2, 3x, something x speed up. But I think the goal is clear. We want to be as fast as C or at least as close as possible. We don't want to be like 50 times slower, 100 times slower where we started out maybe 2 years ago. So the rest of the talk will be about how do we do that. And I think the key concept we changed in compilation to get there was that we rethought the translation unit. And traditionally, when you build a compiler, you build your work on a lot of existing work on static compilation. We have for a long time compiled static languages like C, and back when we started doing that, we needed a translation unit. Machines were not large enough to hold the entire program necessarily in RAM, so we had to pick some kind of translation unit. And a method or a function is a very natural translation unit. It's kind of self-encapsulated. It has a certain way you can call it. It can call other things, but you can translate it individually. And over time, as we built more and more optimizing compilers, we started doing things like inlining to reduce the transition cost between these things, and we could inline functions into calling functions. But at the conceptual level, it's still basically go through all the methods in your program and translate them to something. And the reason that we can actually do that we can take a function or a method and compile efficient machine code for it, is in case of C that all the types are pinned down. I know exactly, without knowing the runtime values, how do I have to generate the code. It might not be super optimal code. There's still profiling I can do on top of that and maybe optimize further. But I already have a pretty good understanding how the values behave because I have their types that are fixed. So in case of Java, for example, if D is declared as a double, we know this is always going to be a double. I can put in a physical floating point register. And I don't have to anticipate any unexpected type modifications. So something like this here simply is not something I have to deal with in a Java world, that I have a condition inside a loop where I add 0.5 to D, which makes it stay a double, and then suddenly, out of nowhere, I assign a string to D. And this would be a really big problem when I come to the return value here, because now I would somehow I would have to decide whether a plus operation means add a floating point number and a 1, which proves a floating point number, or add a string plus 1, which in case of JavaScript would do a string concatenation. Again, in Java, this cannot happen because the compiler would simply reject this as a type error. You're no longer statically typed. D has now some weird polymorphic type. So in Java, the control flow can affect the values as I execute the program, but not their types. And that's basically what changes if you go to dynamically typed languages, is that suddenly now the control flow does change or can affect the types of things. So here, D would remain a floating point value, here would become a string, and then for the plus operation, basically at runtime, you have to decide what to do. Now, there have been, of course, many approaches to solving this, and static analysis is, of course, probably the ideal, in the ideal world, would be the best way of solving this. I just analyze the program until I understand all the different types involved, and I try to infer types, and then based on that, I get almost the same performance as for code where the types are already annotated in many cases. Unfortunately, static analysis is pretty expensive, so even really fast static analysis frameworks for anything more less trivial than the loop I showed initially, that takes quite a long time. And most users will not be willing to wait for that. Just remember the last experience you had running a Java application. It's like 3-second startup. It's not what people want to see when they load a website. So basically what people resort to is they generate generic code. And this code is just like an interpreter able to deal with all the different type settings. And then it doesn't really matter. I don't need static analysis. I just generate hunks of code that can do a plus operation no matter what your particular type distribution is. And what you end up basically is just like a fast way of interpreting. It's the dispatch optimized. You might be inline threading your interpreter, but essentially just generic type code that's at the basis of it an interpreter. So the performance is also limited. And basically, Apple's Quillfish Extreme and Google's V8 VM both are taking this route of generating generic code. Now, V8 is smart about the way it does this and try to basically generate a fast path and then an out of line compensation code for it. But still, at the root of it, it uses generic code that can always handle all the different type settings. The way you do that is, of course, very straightforward. If you have some kind of loop that runs through 0 to 100 and does really nothing, if you write down the code that an interpreter would execute, essentially you start out with boxing the start value into I. Again, dynamically typed language, we have to box things. We have to maintain the type information. So I would now tell us, if you look at it, if you look into the box, that it's an integer type and it has the value 0. And then as the interpreter executes, it would basically have all these different dispatch implementations. So it would have to look, is it an integer, which it is, then take the integer value, add 1, box it, and then you're done. And then it would skip to the next step, which would be now the loop condition, and then would again check, is I still integer? Yes. Is it less than 100? Yes, great, then go to label. And it would loop through this. And this is, of course, disappointing from a performance perspective because really all that ever executes in this loop is the initialization and then basically these two integer cases of the loop. Everything else for this loop never gets triggered. But I have to carry around all this dead weight here, which is particularly painful if you do inline threading because now you have all this dead code lying around. So what we do is slightly different. We basically want to go ahead and really only run the code that we have previously seen highlighted on a slide. I want to run only what the machine really runs, and I want to compile only what the machine really is interested in running for this particular program in this particular context. And this is where the notion of traces come in. So a trace is essentially a sequence of instructions that the machine executes as it is running a program. And traces were introduced sometime in the 90s by Fisher. Later on, they were extended by the Dynamo work to be dynamically recorded instead of statically pre-calculated. And the basic foundational principle is that you follow the execution of the CPU, or you somehow derive a sequence of executions statically, and then you say this is a trace, and as long as execution follows the same path, I'm on trace. And if something happens, if one of the conditions that I originally assumed and speculated on changes, then I have to take a side exit. This means that essentially all control flow decisions, like conditional branches, become side exit points or potential side exit points. And I have to re-evaluate them as I'm running the trace. And if they evaluate differently than I predicted it, then I have to take a side exit and take some compensation code. In our particular approach to this, since loops tend to dominate the execution profile of a program, in particular we are focusing on traces across loops. So everything I talk about this rest of the talk, always, if I mention trace, I always mean loop trace. So let's look at the example code we just had, what it looks in a trace world. Well, we have a loop header, and the first thing you will notice, the initial assignment of 0 to I does not appear in my example anymore. Why? Because it's not inside the loop. So it was one of the 3 snippets of code that we actually need, but there's even no need to have it inside the trace. It's executed once, so whether you compile it or not doesn't really make a big difference. But what does make difference are the 2 operations, the 2 remaining operations that we highlighted. So we have to check whether I is greater than 100, and if so, we have to exit. And this is basically a side exit. So the loop condition becomes a side exit because when we recorded the case that we stay on trace. So essentially, it's a control flow decision to stay on trace, to keep looping. And if that changes, if the program decides, OK, I'm done with the loop, I would like to exit, then the control flow changes, and we have to compensate for that. So if that break ever happens, then we hit some compensation code. And then as you go down the trace, we add that one specific integer case that actually added 1 to the integer number. So in our world, traces always start at loop header, and they all loop back to it. Again, since we are focusing onto loops. And we record these things by simply observing frequently executed loop headers. And we do that through by observing backward branches and just considering targets of these backward branches as a potential loop header. And once we reach a certain threshold, we simply start recording, and we record all the activities the VM executes as the program runs. And we only record those activities. We don't record all the other cases that the VM does not execute. So since the VM only executed the integer case of these opcodes, we are also now only recording the integer case. And conceptually, this means that traces are always entered only at the loop header. And once we reach the same point as we started previously the trace recording at, that's the point we can enter the trace from. But we can have an arbitrary number of side exits we can come back out of. And a side exit is the only way to come back out of a trace. Since every trace is a loop, at the end of the trace, you basically jump back to the loop header again. And the only way to come out of that is for control flow decision to change, which is usually the loop condition, which then evaluates differently, and you take a side exit. The key feature of traces that we take advantage of for compilation purposes is the fact it's a linear sequence. So every instruction on trace has exactly one predecessor. There's never a merging of control flows on a trace. They can be splits, so I can take a side exit, which is basically a split in the control flow, but I can never merge control flows back together. And if any of these conditions ever evaluates differently than I initially recorded, or essentially speculated on, then I have to take a side exit. Now, that's great what I just showed on the slide to extract all these individual cases, but how do I ensure that the types still are correct? I recorded now only the integer case, so I cannot handle, with this machine code snippet, any of the other type distributions. For that, actually, I have to insert additional guards, and we call these type guards. So in addition to the loop condition guard, which I represent now slightly more compact than the previous slide, that checks the value of I being below the loop threshold, I also have to insert these type guards. I have to say, OK, right before I can do that, this case only works if I is an integer. So I emit this guard, ensure I is integer. And then similarly, as I'm incrementing I, again, this operation only works for integers. So I emit a type guard, ensure that I is an integer. And then at the end, I have my loop function, my loop branch at the very end. However, we just said we are only interested in linear sequences of instructions. So if that's the case, and we know the type distribution on top here because we already said ensure I is an integer, we can actually follow, as we're recording, we can follow the operations we perform on values, and we would know exactly that this must be an integer because it's a result of this operation here. So we already ensured that once. It means that on these traces, we can very easily and cheaply, in linear time as we record, deduct types once we establish them once. And we don't have to do this redundant type check. So actually, I can remove the second is integer operation. So this means that since traces essentially specialize the control flow, I extracted one specific control flow path. I remove this complicating property of the dynamic type language that the control flow can change types. I have now one path. If I establish the types in the beginning of this path, for the remainder of the path, the types are going to be unchanged, and I can remove all these redundant type checking operations. Next question is, of course, well, if I can do this, if I can establish the type once and I don't have to check the type all over again, why would I still box, right? Yes?
If there were overflow on the +1, it would suddenly become a double.
I will come back to that in a second. If I don't, please remind me. That's a very important point. So if these types are stable on the trace, why would we box? We said we want to box because we have to represent the type of a value along with its actual value, since we don't really know what the outcome of operations is or what the input types are. Now, if I fix this down, if I made this trace, this static interpretation of the original dynamically typed program, I don't really have to box anymore. I know that the outcome of this and this is always an integer, so why box around? Why take that overhead? And that's exactly the next modification we're going to do. We basically split the loop entry from the loop header and say that when I enter a trace, I look at all the types. And if I want to enter this trace, then I must be an integer. Even if I hit the next time the program counter location, if I is not an integer, I cannot enter this trace. I cannot go to the second trace, but this one is not useful in that scenario. So now at loop entry, I establish that I is an integer, and then I unbox it as a loop entry. So I say I is now the unboxed value of I, just a pure value. And in my loop header now, all that remains is the actual guard that corresponds to the side exit that says now I must be less than 100, the unboxed representation. And all the operations I do become unboxed. So I modify I and say +1. And as long as I'm staying in the loop, I know now at the end of this loop, I is again an integer. So I can go back to the loop header, don't have to box, and don't have to unbox in the loop header. Now for overflows, the plus operator actually in JavaScript works differently in Java in the sense that overflows are not allowed. And there are a couple of different ways how you can deal with that. You can either represent everything in floats, for example, say we don't want to ever deal with integers. We only work with doubles, and even if it's a whole number, we work with doubles and add them, and then that matches exactly the representation of JavaScript. This is something that Lua, for example, uses in their trace-based JIT. We're a little bit more optimistic on this one here. We basically speculate on these overflows in reality not happening, which is probably true for most applications. Like you do not overflow 32-bit additions. I know because I shipped a JIT that had a broken code generator for that particular case, and nobody really found it. Fuzzer actually found it for us. So we can just speculate on this. We just say that we check the processor overflow flag right after the addition. And if that flag is set, then basically you have an additional side exit here that would be taken. The interpreter would re-execute this code, would notice that there's an overflow, do a slow double addition, and everything would work out just fine.
Is double addition?
Pardon?
So for this particular case, the compilation does not keep track of the data flow fact that II is less than 100, and therefore +1 can't overflow?
You can. We don't do that at the moment. You can, of course, do additional optimizations. You have this loop that's very structured. You have an SSA-based representation, essentially, where phi nodes are only placed in the loop header. So you can do a lot of very simplistic optimizations very cheaply. There's someone else has a question?
So you made a comment about the expensive doubles. Last time I looked, that wasn't the case on desktop hardware.
Yes and no. So yes, the FPU is almost as fast as the ALU, or most cases actually it's pretty much the same. So that's correct. In that case, it doesn't really matter for the operation itself, but it matters for the environment around it. If you have operations like AND, for example, or all these like arithmetic operations in JavaScript, for example, they define that you have to run them in an integer world. So if you represent your values in doubles, if you have an AND operation on them, you have to take that double, make it an integer, which is really expensive. You have to follow a whole bunch of branches, decision points, and then an actual conversion, which is also expensive. Then you do the AND, and you have to box back into a double. So I think that's one of the things that made the Tamarind VM really slow on untyped code, that they didn't distinguish between integer values and double values. And every time they had like a crypto algorithm is probably the worst possible case you can think of. Like you're basically just going integer, double back and forth all the time. And of course, when any of these guards fails, we have to now box back, right? Because on trace, we are unboxed. So as you go back to the dynamically typed, not control for predicted world of the interpreter, we have to box everything back into a little box, and then we do that in side exit point, which means that the boxing overhead is completely pushed into the side exit and does no longer appear on trace. Okay, summary traces. A trace is a path through a loop of in the original program. It is steadily typed by pinning down the control flow, and two things have to remain the same. The control flow has to remain the same, which I guard on, and type guards have to still apply. Many of these type guards actually I can hoist out. So most changes of values and types to local variables I can hoist out of the loop and check once and don't have to check them over and over in the loop. But there are also some type cards I have to check on trace. And the example is overflow is exactly that. It's basically a type change from integer to double. I have to check that every time I do an addition on trace. But it's very cheap. It's like one machine instruction, essentially. And the frequent cases that it doesn't have. Okay, the next thing we can do with traces that's really important is that there's no representation of calls in a trace. We said initially that a trace is a linear sequence of instructions that the VM executes, and I follow that sequence of instructions. So as the VM does function calls, all I do is guard that the target of the call is the same as it was previously. And then I can basically just follow and inline the code parts of the inner function call onto my trace. And this means that I can guard conditional branches and switch tables and things like that, but also virtual method calls. So a virtual method call becomes as expensive or cheap than a branch from this trace. So how do you compile these traces? Well, at the core of it is the SpiderMonkey virtual machine interpreter. It's this fairly old, 10 years old C code base. It's implementing a fairly well optimized interpreter. And what we did for that, we attached a little monitor to this. And what this monitor does is basically it's looking for taken backward branches as your VM executes your code. And if you see that frequently, since the code has a general forward direction, if there's a backward branch frequently taken, that usually is a loop header. So we start recording a trace at that point. And the way we do that is we have some starting point where we start off from, and we start following the execution of the code wherever it goes. If it goes to a function, we follow you. When you come back out of the function, we see that, and eventually you come back to the loop header again, at which point we complete this trace, this sequence of instructions, and hand it off to the trace compiler. And since you're dealing with loops only, as long as it's a true loop and not a recursion, this actually means if you go into a function call, you always come back out of it inside the loop, which is very nice because then we can actually optimize away the case where we have to build the function frames. If you go into a loop, you don't build a function frame. If you take a side exit inside, and if you go into a function, we don't build a function frame. If you take a side exit inside a function, which you rarely are supposed to do, then we would build a frame for you as you go back to the interpreter. But for the default case on trace, we don't have to do that. And that makes inlining very beneficial for a lot of these applications. You will see that in a minute on my benchmark slides. So I give this trace snippet, this linear sequence of code that I extracted from this program to the trace compiler. The trace compiler is actually based on NanoJet. That's a piece of technology that Adobe contributed to Mozilla. It's essentially a fairly straightforward compiler backend with one small difference. It can only compile a linear sequence of code. It does not know what control flow is. It knows what guards are and how to get off a trace, but it does not know how you represent control flow and control flow merges. And this makes this compiler actually very efficient. So everything the compiler does happens in linear time in one sweep over the code. And once this compiler compiles the trace for us, puts it into the trace cache, and that's exactly where the monitor looks at every time it sees a loop header. It checks first, do I already have a trace for this? Do the types match? If so, go to the native machine code. If not, consult heuristics whether I should be recording here. Now, of course, you have to build a little bit more logic on top of this because right now I was talking about traces through a loop, exactly one trace. That mostly only happens in academic benchmarks that you have only one path through a loop. And in the real world, you have usually multiple paths you can take through a loop. What we do with that, we organize these traces in a tree form. So I start out with an initial trace and record, and then I run that. And as soon I take a side exit from that trace, I go ahead and start recording again at that side exit point and continue recording until I hit the loop header again. So what I end up with are these secondary traces attached to a trace, and I can transition from them straight from machine code to machine code. They're also traces, they're also linear sequences of instructions, but now I can cover multiple paths through a loop. And I share all the code that's upstream of this split point, and downstream I basically duplicate everything. I record it separately. So the structure we end up with, and I think this is what Michael Franz already talked about at length, so we'll skip over this to the largest degree. If you start with a control flow graph like this, where we have control flow decisions inside a loop, what we essentially end up with is we have some primary trace we record, and then whenever the control flow diverges as soon as we run that code, we start recording additional traces we attach to this. So if we go from B to C instead of B to D, which would be this decision point here in my original program, I basically split off a new trace and follow it, and I re-record E and G, as this new trace encounters them, and then I compile them separately. This has advantages and disadvantages. The advantage is I can optimize now E and G in the context of this particular control flow sequence. So if I know, for example, that a certain value is dead in D, I don't have to allocate a register for it anymore, just because in some other path it might be used. So I can do actually dead code elimination and a couple other things on this representation more efficiently. The downside is, of course, I have just generated twice the amount of code because I had to compile G and E twice. And this can become a problem in certain cases. If you have a lot of combinatory decisions inside a loop, this basically explodes on you, and you have exponential growth of the traces in there. There are fairly easy strategies to deal with that. So basically what we do, we limit the tree growth to a certain number of traces, 16 or 32. If that grows too much, we just say, okay, this is the cutoff point. We will we don't record not any more traces. What that basically results in is that for parts of the path, you use compiled code. For the rest, you are forced to take the interpreter. And that does cost you some in performance. But basically, as long as you have a fast transition out of native code and interpreter, you still achieve a pretty sizable speed up.
So when you overflow your number of trace limit, how do you choose which traces to compile? Is it just per
The first 16 encountered. There's an... first of all, please feel to interrupt me at any time. If I don't stop, then start throwing things or something like that. So make sure I stop. Statistically, you can make an argument that the first things you encounter are the hottest traces in the loop. It's not going to work out always, but statistically it should work out. So if you collect like 16 traces or 32, you have the higher frequency ones covered. That works very well for most programs. In certain pathological cases, you have a program where basically all the paths are equally hot. And in that case, you basically lose. Most of the time, we still speed up. So we have a pathological case that runs a cube and has to walk, like make many decision points, or a game of life where you have to consult all your neighboring cells and count things. And we start further, more complicated optimizations. You basically end up with like a 1.5 speed up of the interpreter, since you take some path through the native code, but you also pay a heavy penalty since you have to basically go back to the interpreter all the time.
And what happens if you have a try-catch or something? You have a method that has a try-catch and you're implementing it.
So there are multiple ways to go to look at that. If you assume that your language try-catch are rarely executed, that logic, the catch logic, should never appear on trace, right? So basically, whenever there's something that can throw an exception, we have a guard that checks for that condition. So for example, let's assume you do memory allocation and you're out of memory. Then right after the memory allocation, we check. And if a memory allocation error occurred, we leave the trace, go to the interpreter, and the interpreter always re-executes the last instruction that the trace code failed to execute. And I would re-execute it, would get a memory allocation error, and then actually throw.
Then you have to reconstruct all the frames that we have.
Yes. Every side exits, since we inline into function calls, always imply that if you exit from, this is called the deep exit, if you go into a function frame and exit from there, we have to reconstruct all those things. But first of all, we would have to construct this anyway, right? Even if you construct on the fly, you have to construct at least once. Plus, it's not more expensive than doing it that way. So that's a pure win. There's no case where that would be slower. I think. Right.
Behavior where you consume up your first 16 traces and then a new phase the program starts that's calling the same function and then you've used up all your traces?
So we have actually a submission to PLDI on phase detection using trace trees. It seems to work very well for a certain set of programs. That work was done on Java, but basically the idea is you grow a tree, and we have observed that trees tend to complete very quickly. So you get the first trace, you size it very soon, you get a second one, third, and after a short period of time, a couple of traces attached, you tend to stay in a native code, especially if not all the paths in the loop are taken. And then basically you can close the tree. You just will no longer extend it. After a certain amount of time passed, if you see a side exit, and especially if you see frequent side exits, you can assume a phase change happened. And you can just go ahead and trash the tree, throw it away, re-record. The key point of trace compilation is that it's extremely fast. So in most benchmarks I will show you, compilation takes literally microseconds, because it's just a linear sequence and very few steps to do. So you can afford to throw things away optimistically. Like if you think, this looks like something changed, maybe I get a better tree next time I compile, then you throw it away, re-record, recompile, and there you go.
If A, B, C, D, E, G is the primary trace, and let's say that
A, B, C, D?
A, B, D, E, G,
Okay,
sorry.
yeah.
And if then you do C, E, G.
Yes.
If there are register allocation decisions made, are they recorded in such a way that the compilation of C, E, G can respect them?
Yes and no. That's not the no part. So when we initially assemble these things together, we want to generate code very quickly. We want to switch from interpretation to compiled code as quickly as possible, since the speedups are very dramatic. So what we do is we generate code for this initial trace, and then if you attach a second trace, this trace basically writes through to memory all its values onto a virtual stack. And at any point, any of these guard instructions, we can simply exit to a different trace, and this trace loads the state from memory. So a transition from B to C would involve to memory from memory stores and loads, whereas from B to D, you would have pure register transition. And this, of course, is costly. So we do this initial stitching of traces, and then in the background, we can fire off a compiler thread. We can actually go over the entire tree, and if you have an entire tree where you already know all the traces, if you walk the tree in a certain particular order, you can actually generate a resource allocation that matches all these points just by walking the tree once. The reason you can do that is that we don't have control for graph merges. So it's like an iterative data flow algorithm, just like the first pass is going to succeed because there's no merging that forces you to redo something.
How is the garbage collector looking for traces?
We use a simple trick for garbage collection. We never collect on trace. So anything that might cause a garbage collection simply returns an error, and we have a guard that checks that the error condition occurred, so for example, out of memory. If that happens, we leave the trace, we go back to the interpreter, we might have to restore frames and a couple other things. Then the interpreter re-executes the allocation, and the interpreter knows how to enter a safe point state and then have the garbage collector free up some memory. So essentially, we preempt the currently running tree if a GC happens and let the interpreter worry about it. And then when the interpreter is done, it will go back to the loop header eventually and then fall back into the trace. And this was, in the beginning, just basically a simplification to not having to deal with the different complexity of garbage collection. But actually, I think it worked out very well for us. So even cyclic garbage collection from a different thread works very well. We actually have guard instructions at the end of the trace that allow us to preempt traces. So I can set a flag in a system that says all trees please end and go back to the interpreter. And then if everything is in the interpreter, then the GC can preempt those threads and enter safe point states. Okay, I will skip over nested trace trees in the interest of time and about the register allocation on traces. And I will get to the part that everyone is interested in, usually. Benchmarking. So benchmarking is basically the art of like selling what you have and making people believe it's really superior. And I think we see a particularly bad case of that in this current JavaScript environment. Somehow JavaScript performance over the last 6 months has become this like new focal point of the new browser wars, in quotes. And I think it's particularly tragic because we miss the most basic ingredients, like mature JITs, benchmark sets, or even proof that in actual applications like Zimbra or Gmail, JavaScript performance matters. So the first problem you run into if you try to benchmark in this environment is that basically there's one established benchmark. It's called SunSpider. Some people claim it's not a very good abstraction of what the web really does. It's basically Fortran code translated very poorly to JavaScript. And that's just not necessarily what the web does. So making that run fast in many cases is really difficult because also the people who wrote that benchmark didn't really understand JavaScript very well when they wrote the benchmark. So there's some very awkward uses of language features that don't really are not really the frequent case, but you have to make them fast anyway. And then, of course, did not go unnoticed to people who build VMs. So when Google built their VM, they must have noticed, oh man, we are really slow on like SunSpider, so let's make our own benchmarks. And they're actually very fast on their own benchmarks, and I think they're still the fastest on those. But actually, the performance on SunSpider is really not that fantastic. But academically speaking, it's probably kind of questionable, but that's the right way of like just writing your own benchmarks if you're slow on somebody else's benchmarks. What we really would need is some decent, grounded in like product realities benchmarks. So make Zimbra fast. And that brings us to the second problem is if you look at actual web applications today, your JS engine is a very small fraction of that in most applications. A lot of time is spent in the DOM rendering things, interacting with the DOM, transitioning in and out of the JS engine. That argument, I think, is over time going to be weakened. So I think it's fair to say if you make the JS engine faster, people will come and find uses for it. So if you make the JS engine faster, that's always good. Even if right now it's not a huge part of your profile, it will become over time certainly more in demand. I will try to show some comparative benchmarks, how the systems compare, and mostly I'm interested in showing you the fundamental differences, not really the exact engineering differences. And it's very difficult to do that. So this is a very volatile environment, and people release new versions all the time, and there's absolutely no way to give you a fair evaluation of what the others are doing. So this is really not meant to like disparage any like the qualities of Scopes Extreme or V8. I'm just trying to basically highlight conceptual differences and where I think that we have conceptual advantages or conceptual disadvantages. a lot of the details are actually engineering parts. So people have different emphasis on different parts of VMs, and they perform differently and different benchmarks. But I think there's some core observations we can make anyway. So here's a comparison of Firefox 3.1, which is the new version of Firefox, which we have the TraceJIT, and Firefox 3, which has an interpreter. So you can see the speedups here ranging something like 30x on that particular benchmark. That does basically some bit manipulation in a tight loop inside a function. This huge speedup is mostly the function called inlining that we do. We don't have to build the function frames. They dominate execution cost of that in interpreter. We don't do that, so we get very nice speedup. And as I go down, you can see that performance speedup goes down to like 2 point something on Funku. These are all different benchmarks. They basically access at different parts of the VM. And actually, there's also a bottom part of this graph. This kind of shows you this is a fairly incremental approach. So there's a lot of benchmarks where we get good speedups, and then it goes down to some benchmarks that don't really speed up. Recursive, for example, is just basically a recursion over a tree. We don't implement, at least that time, we didn't implement recursion in this approach. So basically, we don't speed it up except for like one little loop. It does some evaluation and statistics at the end. There's regex DNA. Regex DNA spends 100% of its runtime minus like 5 JavaScript operations in the regular expression engine. So you can make your JavaScript as fast as you want. You will not speed up regex DNA. The only way to speed up regex DNA is if you build a regex JIT compiler. And as I let in with that Apple actually just did that. So that's basically now if you want to compete on these benchmarks, and this benchmark is a really large part of your overall score. It's just like 20% or so. Basically, this means that if you want to compete with the big boys, you must have a regular expression JIT compiler. If it's already hard to argue that right now JavaScript is a really huge part of the web experience, but the regular expressions are a big part, nobody really knows. What you would really need is like some founded research that shows, yes, regular expressions contribute to n% of my profile, and JIT, just JavaScript is so much. So basically, this also shows you somewhat the limitations of this benchmark. Format export, by the way, is also very regex heavy. The other thing that you can see in this graph is a very incremental approach. So basically, if you trace something, you can implement a subset of instructions initially. And then later on, you add in more and more opcode as you go along. And basically, if you see that, OK, I'm so off last time because I fall somewhere off trace because I don't support something, you can always just abort recording if you don't support an opcode. You can let the interpreter deal with it. But of course, your performance slows down. So then you can go back and add an opcode or add a certain specific case for the opcode, and then you start making things faster over time. These numbers are like 3 months old now, so they're probably not. This binary trace. So in recursive, actually, there's some loop that we manage to compile. In binary trees, we don't compile anything. So here's simply the monitoring overhead makes us slower than the interpreter. This is the monitoring actually is pretty cheap, and we have very fat opcodes, and the interpreter is really slow. And so this is not even that's not really a 10% overhead. It's like a 3% overhead or so. You can get a couple percent overhead. If you don't trace anything and you just monitor, then you will have some performance penalty.
What about the control? Like, what's so special about the code itself, like the code?
This one, it's simply recursive. We're not. It's just recursion. This version of the JIT only did loops, explicit loops and syntactic loops in JavaScript, not recursive loops. And then we also run a couple of like micro benchmarks, just to like show basically what the limits, what kind of maximum speeds we can expect. And the biggest improvements are like empty function calls, like that's like a 20% speed up because we don't have to build these really heavyweight function frames that JavaScript usually builds. Empty loop with globals, 40 times speed up. Globals are frequently mistakenly accessed by JavaScript programmers. So if you don't say var in a function and don't declare something explicitly as local, it becomes basically part of the global scope. And you have to like reach into the DOM and like manipulate the documents globals, and that's pretty expensive. So if you optimize that well, you get a very big speed up. And then I guess this is the part where really everyone is interested in. If you look at performance comparisons between like V8, Skillfish, and tracing, you can see that it's very mixed all over the board, basically. So sometimes V8 is fast, sometimes V8 is fast, sometimes Skillfish is faster. But I think the cases I'm really after, like academically speaking, is something like this here. So the blue one is the tracing one. I think we can show that for certain cases, we have significantly better performance than the competition. And I think that the underlying reason for that is that we do type specialization. So as long you have to box, as long if you go between instructions, you have the generic code patterns, you do not type specialize, you will always have box and overhead, you will always be limited. Second, and on top of that, and I think you see that most in these two cases, which both do inlining, we can do inlining very cheaply. And the reason that the other approaches don't do inlining is that the generic code patterns are already very large. If you do inlining, you do further code duplications, so they already have a bad code cache utilization. If they do inlining, it would get even worse. So my impression is that if you just do a purely inline thread interpreter, inlining is going to be very difficult for more complex cases. And we can do that very cheaply because we extract only this one specific type case. And we can very compactly generate code for that. Okay, so I guess the summary of this is that if you compare us with the competition, there's a lot of engineering differences, to be honest. And especially Squillfish is very impressive for this mostly inline threading interpreter. It has a very fast interpreter already to begin with 6 months ago. On top of that, they added now this inline threading code generator. And it was back then 2 times as fast as our interpreter, maybe it's 3 times as fast now. And they still stick with the disadvantage of that approach though. So they have generic code patterns, every operation can support every type, since you cannot really do reasonably static analysis ahead of time. And basically I see that as the best of the breed in interpretation. So if you do all the tricks that Apple does in Squillfish Extreme, that's the fastest you can get with interpretation or with generic code generation patterns. And we are significantly faster than that. And I think that's the only thing we should really take away from this talk, not the little number differences that if you don't type specialize, which you cannot do if you don't do some kind of more specializing approach, then you will be limited in what you can do. And we can go beyond that limit. And in some cases, you have like a 12x speed up over Squillfish. And that's probably half as much, like 6x over Squillfish Extreme. And I think the comparison is very similar to Google. So the little differences, I think that's mostly engineering differences. Who has what garbage collector and what string representation. But there are some things that stick out. Like these 2 cases stick out. This is recursion. So access binary trees is recursive. Control for recursive is recursive. But you also have these cases where we have like a 4x, 3x speed up over V8. And for V8, you have to keep in mind that's really that's a VM designed from scratch by people who know what they're doing. And I would assume that that's basically the best of the breed code generation you can do with generic code patterns. And then yet we are quite a bit faster on some benchmark cases. So basically this one here, these cases we have to fix. We have to trace recursion. And these things here are just engineering margins. Here I think there's going to be a certain convergence as people understand better what kind of garbage collectors you need, what kind of string representations. So little things are going to go away over time. But what's going to remain, I think, is that in some cases you get the best speed up through type specialization. Okay, so I present today in my talk trace trees as one method to type specialize dynamically typed language code. By extracting these traces that are essentially a path through a loop, and I introduce this trace tree structure that can extract more complicated trees of these paths. And the key concept behind this is that traces allow us to extract a type stable fragment of code from a dynamically typed program. And I do that by pinning down the control flow. Once the control flow is stable, I can eliminate type checks further down once I've established once that the type is stable. And even more importantly, across the loop edge, I can assume a certain fixed typing. And the code I generate starts to look very similar to actually steadily typed language code that's generated by traditional static compilers. And that basically explains this one graph, this one example I had up here, where it showed that we can get fairly close to the performance of something like C for some cases.
Have you given some thought to combining the 2 approaches, basically the Squillfish Extreme approach with this approach, so that instead of having an interpreter at the core, you would have fast generic code that was doing monitoring and then specialized for
So if you look at the numbers, it's absolutely clear our interpreter is too slow. And tracing is really great for peak performance, but it cannot cover all the cases. And we have talked about 2 of them, like the cube example and game of life. So we need a fast interpreter. We need a fast baseline interpreter. We cannot make up, no matter what kind of peak performance you have, if you are really slow in some cases. So I think what engineering-wise has to happen is that V8 and Squillfish Extreme have shown how you build a really efficient interpreter. And we need to have an interpreter that's at least as efficient. And then on top of that, tracing is basically everything is pure profit.
And when you say interpreter, you would include JIT compilation of the
Squillfish Extreme is an inline thread interpreter. I mean, you can, for marketing purposes, you can probably argue about it, but I would say Squillfish Extreme is an inline or context threading interpreter. V8 is probably a little bit further on the compiler edge. It's not really an interpreter anymore, but it's almost an interpreter. But yeah, generating code patterns, either pure interpretation or ahead of time, very fast, unoptimized code generation. Any of these approaches that generate good baseline code that makes the interpreter as fast as possible.
You didn't address type transformation. inside type stable. That was
okay, let me see if I have a graph for that. Probably not. Okay, then let's just do it like this. So basically what can happen, of course, is that if you look at dynamic type languages, there's no contract that types don't change. But in practice, they tend to not change. If you have loop counter I, you use it for a loop counter, you will not randomly assign a string to it. It's very rare, usually by mistake. But there are, of course, cases. Like you have elements in a hash table. Sometimes they are null, sometimes they are objects. Those are two different types, for example. So in that case, we have to split the trace, and we record two different traces. That works without any problems in the scheme as presented, as long as at the end of the trace, none of these values is alive. So it's perfectly fine to take a value out of a hash table, do something with it, as long as it goes dead. If you have actually a loop carrying variable where you change its type randomly, then we have to be a little bit more smart about this. Basically, what we end up, we have multiple trees on top of each other, and at the end of each tree, of every tail, you can cross jump. So if something is an integer at the end of a tree, but you start it as a double, and you look for a tree that starts with an integer, you can just jump there. So you can basically cross-connect these trees together. Okay, who's next?
Is there a simple explanation why your speedup is so much bigger on SHA-1 than on MD5?
Yes. MD5 uses a regular expression inside the innermost part of the crypto loop to parse characters into bytes. It's, again, these benchmarks are not very well written. And this is one of the things we're fighting with. We had to make really, and it's even worse. It uses a regular expression, there's a lambda function in it. So you have to make a lot of corner cases really fast to compete on these benchmarks.
Do you have a sense, relatively, especially in a more complex website, of the overhead where you're interpreting versus the amount of time in garbage collection?
We have a very, 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 very poor garbage collector. So if you garbage collect a lot, we would lose out very badly. In my experience, what I've seen so far, it's a fairly rare event. So if we garbage collect, we enumerate certain internal data structures, which forces the code cache to be flushed. So every garbage collection always implies the code to be thrown away. It's not a huge problem to recompile since it's very, very fast, but it definitely, the garbage collection itself is a pain. It's also fairly slow. It can take dozens of milliseconds to garbage collect, or worse. Garbage collection usually happens in a ballpark of 30 to 45 seconds as a tab is running, so it's not a super frequent event.
It happens every 30 to 45 seconds?
It can happen every 30 to 45 seconds, yeah. There's also a heuristic that tries to garbage collect basically aggressively to reduce your memory footprint.
You always seem to lose with recursion. Do you have a strategy for making recursion faster?
Yes. So the reason that we didn't do recursion goes back to the fact that we started with a regional compiler that was doing Java, and we knew very well how to do syntactic loops, and we didn't really fully understand how to do recursion. Principally, it's not harder. It's like you have a function entry, which is your loop header, and you go through it, and you come back to the function header at some point. The only conceptual difference is that you have, instead of the perfect zero balance of stack frames, you have one or more stack frames more. But you can deal with that fairly efficiently. So in the newer version, we actually do that. Actually, yeah.
Did you extend the debugger support for traces? Do you step into traces with the debugger?
Yes and no. There's some work on it. I don't think Firebug right now works very well. 2 months ago, we were crashing it horribly. We don't do that anymore. And there's actually some improvement along the way. If you set a breakpoint, we throw away the code cache and we compile. And if you compile and come across a breakpoint, we basically emit a guard that always fails. So you can actually stop inside traces, and you can inspect things. And the guard basically forces you to go back to the interpreter, so you have the full functionality of Firebug. So actually, this works very well as debugging. It was not really a high priority in the beginning. In the beginning, was basically just like make stuff fast, prove that this works.
For your recursion implementation, conceptually, you could treat a simple tail recursive loop as essentially a loop and get tail recursion optimization, tail call optimization. Is that something you're looking at doing?
So in our hotpath compiler, that was the Java implementation of this. That was the only kind of recursion we supported, was tail recursion. Tail recursion back to yourself. And that actually you make it look like a loop, essentially. It's a go-to back. You can prove that you don't need a stack frame for it. I'm currently working on the recursion implementation for JavaScript. It's a little bit more complicated, but it also supports more cases. So we can do mutual recursion and non-tail recursion with that as well.
And how do you handle stack population across a trace that's kind of going back to what's conceptually a called loop header across maybe multiple recursive calls?
So basically, you pick something as a loop header and record across that until you come back to the loop header. And you might sometimes end up picking actually the wrong loop header or picking multiple loop headers along the same chain, depending on how things get hot. Eventually, one one of these constructors is going to win because we'll cover all the other paths and will not get hot enough anymore to be taken. The bigger problem for us conceptually is that we have an interpreter stack and we have a native stack. And we translate a trace entry from the interpreter stack to the native stack. And the native stack is unboxed, which means that if we are doing down recursion, we build these native stacks. And then let's assume we have one trace that goes downwards in the recursion, and then eventually it hits a side exit. It wants to take a different control flow path. Now we have to deconstruct all these native frames, make them interpreter frames. And now, once we recorded this one case, we enter the native code. It wants to recurse up, but there are no native frames. There are only interpreter frames. So that's going to actually force us to side exit a whole bunch of times until they come back up in the recursion. So if you just have one recursion down, back up, we only speed up the down path, not the up path. In most of the applications, usually recursion tends to be taken more than once down and up, so there you should be fine. Back there.
So a question about offline compilation. You mentioned that they do some offline compilation JavaScript on the server side with that Rhino tool. My question is, so this requires browser support anyway to be added, so why not just add browser support for offline JavaScript compilation?
Well, this goes back to, like, if you try some personal experience, if you try to submit on JavaScript, for example, a paper to an academic conference, the first thing everybody will tell you is like, why do you use JavaScript? And I think it's a fair criticism because the language is a little bit funky. We have seen all these weird properties of it. But I think that's the wrong academic view. Like, I completely agree that JavaScript is not the most ideal language choice for a certain set of applications. But you're not the ones making the choices. I think people like dynamic languages for some reason, and we have to live with that. And yes, maybe it would be nicer if there was a binary representation format for it. That would probably work. And there have been some talks about that. There's also counter tendency. People like the source format. You can copy and paste. It's very open. You certainly don't want to go native code, right? ActiveX, we all remember that. You don't want to like ship around native code and have to sign it and trust people based on signatures. You have typed assemblies. There are certainly alternative approaches. I think it would be difficult to replace 1.4 billion browsers that have JavaScript in them. So that would be there's a compatibility problem, and there's also just this. People like. Sure. But also it's an open process, right? So let's assume we do that. So Microsoft's going to do it in IE, which is like the 70% of the market. So you have to get everyone in the same boat. Everyone has to do the same thing. The process changes. Right now you can go to the website, change a little script, and then suddenly the application is different. You would have to recompile, sign again, typed assembly. I'm not saying it's impossible, but basically, I build JITs. I make stuff fast. I restrict myself to that particular area of it. I think it's necessary. I think I've shown that we have to do this right now. There's probably long-term strategies we should look at, but there's no alternative to making the current text-based JavaScript and server-side PHP and all these things fast. And then on top of that, we should probably look at other alternatives as well. Yeah, it's also for compactness reasons. Like, the source code is not very compact. It should probably be compressed or something.
You have a slide on mobile devices itself.
Yeah, I felt bad for the time using them, so I skipped over that. So basically, we also have an ARM backend, and more recently, we also just got a PowerPC backend. And we see basically very comparable numbers here, up to like 30x performance increase in some cases, and then less performance increase for others. The performance profile looks very similar, except for machine-specific differences. The key point that the slide is trying to tell you is that we can do ARM, and we can do it with very little overhead. So this was basically just a side project. It's not a big priority at the moment. Mozilla is building a mobile browser, so for that it's interesting, but the main platform really is x86. The reason we were able to do this very easily, we started to re-engineer the JIT in a large fashion, is that the machine code we generate is very compact. We have this little snippets that do type-specialized cases, and it's not a lot. It's only for loops, not for the surrounding code. So we have a very favorable code cache utilization. And I think it's going to be much harder for these kind of environments to use the generic code patterns, because they are much more comprehensive. They're much larger to deal with all these different cases. And there you have much worse code cache utilization. So if you have platforms where memory matters and energy and smaller caches, I think our approach is certainly very favorable there.
What you just said about how does that mesh with Squirrelfish on iPhone?
I don't think that Squirrelfish isn't. It's because it streams on iPhone. Squirrelfish might be. I don't know about that. I think initially the iPhones shipped this web core, which is the very old AST Walker. They might be using Squirrelfish now. I don't think they're using Squirrelfish Extreme. That would surprise me. We can't really do comparative benchmarks on iPhone, unfortunately, for legal reasons. Google might allow it in a G phone eventually.
Do you have any benchmarks for which you can measure the sensitivity of performance to trace cache size?
We have not done that work yet. We really should do that work. So keep asking the questions. If you ever review one of my papers, ask that question, and then that's going to force me to do that. We should, yeah. I did some work on that in my Java implementation, and I think over spec JVM, I had 300 times less code cache utilization than the hotspot client compiler, I think. It's pretty obvious. We picked this like small little snippets. It might be different here, a little bit less favorable, because we have sometimes multiple copies of the loop. On the other hand, we have these very small snippets in comparison to generic code. So we should do the comparison, yeah, definitely.
Real Ajax sites, did you see any significant improvement?
You can measure improvements. Significant depends on a particular definition of significant. It's mathematically significant. For practical purposes, I think there are few, like Zimbra or something like that, does not speed up significantly. I have seen speed up in Zimbra in Google Chrome, for example. There, it's not coming from the JIT, I think. It's coming from a very fast path, transitioning from JavaScript code into their DOM code. So there's right now the application profile is dominated by like DOM rendering and transition from JavaScript into DOM. All those paths have to be improved. Once they are all ideal, I think just by that we will see improvements, or we will see more exposure of JS performance to these applications. Of course, if you write code explicitly with the intent to do some actual application logic in JavaScript, you might see bigger improvements. We had a demo a couple of months ago where you do like image manipulation. You change the contrast of images in JavaScript, and there you see, of course, a huge speed up, like 7x or 10x or something like that.
I've heard that Mozilla is working on a project to re-implement significant portions of Firefox in JavaScript. Do you know more about what's going on with that, and is that partly because it's expected to synergize well with the work you're doing?
I think, so I'm on the VM side of things. I have very little exposure to the actual browser decision-making process, but my understanding is that already large parts of the browser are written in JavaScript, and I also know for a fact that we JIT very little of that. And I think the reason is that browser startup time, a couple of factors like that are very important for the product, so that's very optimized. And if you have a slow interpreter, as you had 6 months ago, and you have a lot of JavaScript code you have to run through, you make sure you run through as little JavaScript as possible, and especially you don't do anything loopy. So in the entire browser startup, there are two things we trace, because all the other loops were removed and expressed as C code that you call from JavaScript. So there might be a trend now to do more in JavaScript, because actually now if you can do things in JavaScript, if you save transitions into the C code, which are very expensive, there's like a component-oriented model behind it and marshalling of data types. So if you avoid that transition, you can actually save time. Even if the C code would be a little bit faster, the transition that you save makes up the time. I don't think that's going to be like a huge engineering effort. It's just for a product, it doesn't really pay, right? If the C code works well, why go and like break it? But you can certainly do more things in JavaScript, and there's definitely an interest in doing more, especially in interfacing with the DOM. So if you store properties in DOM nodes, maybe you want to store that on a JavaScript side now.
I have two more quick questions. One is, when do you think you'll have numbers coming out of the recursion optimization work that you're doing?
We have a third beta scheduled for early January, and I was hoping to make that beta for the recursion implementation. If we don't make that, then basically there might be a decision to hold that back, since it makes more things trace and might break things. Then basically right after the beta 3 comes out and the product is finalized, right after that you would see it in our nightly build. But if you're interested in any of these features, we have a fairly open developer model. So you have like a bug tracking system where these things are tracked. You can see my patches and try it out for yourself. I will probably do an academic paper on recursion tracing. So that should be also sometime early next year.
And what do you think about trace trees in the long term as kind of competitive against heavily, profile-driven static optimization? Sort of where do you see that kind of arms race going ultimately?
So in my dissertation, I did this like small embedded systems compiler written in C, and we rewrote that from scratch in Java, targeting Java as a more heavyweight system, try to compete with heavyweight optimizing compilers. And I think we got some promising results for certain cases that we pick. We also lose in a lot of cases. And I think to find a good system-based proof that you can really be fast with trace trees, the overhead you have to put in is quite significant. You have to build a complete compiler that understands a whole bunch of optimizations. And we know how to do certain optimizations on traces. We can do escape analysis. We can do partial redundancy elimination. A lot of fairly advanced techniques, but you have to implement them all. And that's a smaller part of it. Then you have to do things like garbage collection and the object model. So between the resources available to like academic research and 1 or 2 grad students, it's fairly difficult to prove, basically create this like wander JIT that's like faster than hotspot in all cases. But I think for certain code we can show that. Yeah, we do the tail duplication that we do. Just it can be expensive in certain cases, but for a lot of cases it actually makes the code generate quite a bit better.
You talked about specialization as being too expensive to do in a JIT context, but isn't it more like a spectrum? Like essentially, you could break up the two. The trace thing is doing 2 things. It's collecting information, like profile information essentially, and then it's doing optimization. But you could theoretically do other kinds of specializing without, for example, doing traces, right? You could just look at code and replace functions wholesale, for example. So have you seen people doing that? Have you compared with those ideas?
So to a certain degree, that's what V8 does. V8 does inline caching, basically, of specialized cases. So if you have a function call, they try to observe where the function call usually goes to, and that's the fast path they encode. They check some condition. If the condition holds, they take the fast path straight to the called function. Right. They don't do the other thing you described. So if you really want to do any kind of reasonable type analysis on JavaScript, you would have to do this in an interprocedural fashion. And I'm not aware of any online approaches to do that. There's some work coming out of Berkeley. They do some Python-based static analysis that's reasonably fast, as in like dozens of seconds for realistic programs. And that might be something you can do in an online context, where you like have just staged compilation. So you do very fast interpretation. Next stage is trace compilation, and then maybe that you have this heavyweight analysis that runs in the background in some separate thread. So that there's potential for these approaches to work together. Static analysis, I've not seen really instantaneous enough approaches. So I think that's an open research area. There should be more research on very fast, very aggressive static analysis that tries to prove at least some properties. And no matter how small the property is you can prove, I can actually take advantage of that, and I can turn a speculation into some known knowledge and better code. Any other questions? Okay, thank you very much for your attention.